Okay, so hi guys. Today I would be solving two types of dynamic programming problem. Why I'm doing this is because I've seen similar kind of problem coming up in contests, and I think maybe they could even help you with interviews. I won't say that these kind of problem would come in everyday regular interviews, but in high-end interviews like Google, Facebook, Netflix, maybe. So yeah, and these could be tricky for few of us, and so I thought let me share my thoughts and tricks like how to solve these kinds of problems, and maybe that helps you. So that's basically the motivation behind it, why I'm doing all this. Okay, so I'll start with the first problem, which is I would say comparatively easy, then we'll jump to the next one. And the first problem goes like this. So it is from educational DP contest from AdCoder, and the problem is matching. It's the problem matching, and the problem statement goes as, I'll read it through. So there are n men and n women, both numbered from 1 to n, and for each ij, both belonging to 1 to n, the compatibility of a man I and woman j is given an integer aij, given as an integer aij, and if aij equal to 1, both are compatible, and if it is 0, they are not compatible. Now you're given n pairs, and each consisting of a man and a woman who are compatible. Okay, and here each man and each woman must belong to exactly one pair. Okay, and find the number of ways in which you can make n pairs. Alright, so as we know, and all values are input and n is 21. Okay, right. So so the problem basically boils down to is they have given us a matrix in which ones and zeros are there. One basically means ith man is compatible, and if it is aij is 1, so if aij is equal to 1, that means ith man is, that means is ith man is compatible with jth woman, and if it is not, they both are not compatible. So now we have to create every possible pair, and we have, since it could be a big number, we have to modulate it with 10 to the power 9 plus 7, which is the biggest prime in integer range. Okay, so now what next is, so how do we solve it? So basically, if I can say, so basically if there are n man, alright, so let's just say for now, for simplicity purpose, let's say all are compatible with everyone, all men are compatible with all women. So basically first man will have 3 options to choose from. Similarly, the second man will have the next 2 options to choose from. Third one, unfortunately, will have only 1 option to choose from, or it could be vice versa. so 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 the basically uh, so so for, and it could be as big as 21. So this size could be as big as 21, and so how we will do it is basically, uh, we have to know like which all, so if we are going through by the problem statement, by man selecting a woman, we have to know which all women have not been selected and which all have been selected, because then only I can check with the compatibility status and then resolve the recursive statement, and we can memorize the recursive statement, and then it will become a DP problem. That's it. Okay, so let's jump through the code and let me go through one of the input. Okay, so let's just copy this. Okay, so now let me just this will be needed. Okay, so let me just say int n cn, and let me just initialize it. Integer matrix of would be of as big as 21, so let's just make 25. is 25. Now we know this. So how we would be actually knowing, so yeah, okay, so before I write the DP state, so I would be actually knowing out of these n women how many have been selected and how many have not. So for that we, so one of the thing is like, okay, so if we have an array, let's assume if we have an array and we say, okay, whichever woman is selected, I mark it index as 1 or 0, whatever. So we can use this array to know in the next state that, okay, so this one is selected, I cannot, so we need to, so the condition says over here, we need to have exactly each man and each woman must belong to exactly one pair, so we cannot have duplicacies around that, right? So we need this. So if a woman is already selected, we cannot select that woman with some other man, right? So we would need this. And so so if so in this case array looks fine, but then in the recursion, if I pass the array, okay, I can pass that also, but then the problem would be when I'm trying to memorize it, I need to memorize it, otherwise the recursion would keep going on and it could be a problem for us, right? Like it would branch out to many possibilities, and then the answer would be in exponential terms, which we don't want, right? We want to have the best possible answer. So how to memorize this array? The problem next comes up is this. So as we can see, there is a reason with the constraints is also important. 21 is not a big constraint, and we can use bit masking in this case. So what I mean by that is basically for every bit I can say 0th bit means 0th woman, first bit means first woman. Alright. So similarly for every bit we can have the array indexes associated, and these bit would be as big as 2 to the power 21, alright, which is something around 2 to the power 10 is 1024 square, 10 to the power 6, right, something around this. It's 10 to the power 6, which is possible in an integral range, right? And then so our time complexity would be, and then we will iterate over every man, and that is just 21. So our time complexity would be well within the limit, right? 10 to the power 6 into 21. So that's the basically idea behind it. So we will have a DP state which can have, let's just say 21 nulls, put it this much, and one left shift 25. Let's not make it 25, 22. Yeah, this much I think will work, yeah, because then 25 would be a very big number. 22, 20, and 21. Actually, will I be even needing 21? No, I don't think I will be. Why I'm saying is, this is because if I'll shift left 21 times, it will become 10000. It's basically 22 digits. I just need 21 digits, right? So that's why this will also work, I think. Okay, so that's there. Now let's input the matrix. We have taken the matrix input now with us, and then Let's just start with a dp state. I'll mark it as a recursion. I'll mark the recursion as a kill statement and then pass it with. So I'll be starting with 0th index from the first man, and initially let's just say all bits 1 means if a bit is 1 means not yet selected, right? So initially all the women are not selected, so we will have 1 to the power n minus 1. So basically what I'm doing by this is, let's just say if I want to, so let's just take an example of 1 to the power, I shift left shift by 2. So basically when I shift it by 2 I get a number this, right? And then if I subtract 1 I'll get this, right? So basically this is 2 to the power 2, which is 4, which I have signified by this, and when I subtract 1 it becomes 3, in which all the bits are 1, and we want this only, right? So over here 2 and 2, right? So these two bits would be signifying women who are, if they are 1, they are not yet selected. So this is there, and then let's just write this. To mask. So let's write the base case. So if we have reached the last index, like we have selected all, so we are done with all the men, and now we just want to see all the women must be selected by now, right? So if mask becomes 0, then it's a true state, right? Then we have got one valid matching between all the pairs, right? Otherwise, if still someone is left, if some woman is left, mask won't become 0. So whenever a woman is selected, we will make the bit from 1 to 0, right? So whenever, if the mask is not yet 0, so finally all the women will be selected, so all the bits will be 0, so mask will become finally 0. And if it is not 0, then that means maybe some women have not been selected, and which is not a valid case, so we'll return 0. It's not a valid way of matching, right? Now once that is done, okay, so we will have, so we need to have our dp state resetted, and then for that we can have size of dp. So basically initializing the dp. So that means if dp of idx comma ma is not equal to -1, this, if it is equal to -1, we haven't visited this state, and if it is not equal to -1, we already have the answer for this state, and we can just return that. So we won't have to do the recomputation again, right? So we have just selected, so we have just done the memoization part, and now let's just, so now what can be done is, okay, so for every woman j equal to 0, j less than and j plus plus, we will first check if that particular woman is compatible with this particular man idx comma j. If it is compatible, and that particular woman woman should not have been selected, right? Should not have been selected. For that, we have to check the mask, right? And how we'll check that is, if if she's not selected, then that bit was needs to be 1, and then this particular woman is jth bit, right? Jth woman, 0 zeroth woman is like first, and then I can actually have I think so. 1 left shift by 0, 1 left by 0. Okay, yeah. And then 0th bit is selected. Yeah, I was just confirming in my mind. Okay, so this works. Yeah. So so what I was thinking is 1 left shift is 0. We'll say the first bit, and if the mask is 1 on the so basically we would be, so let's just say mask is something of this sort right now. Then what I would be saying is, initially there is 1, and we just have shifted it left only 0 one step. So if these both bits are 1, then the answer will become 1, and then that is true. Otherwise, if it would have been 0, then the answer would have been 0, right? So if that particular woman is not selected, then this is a possible matching, and then we will just pass it to the recursion. It will be kill of idx plus 1 going to the next man, and with the mask we have to mark this this particular bit as it has been selected. So since it was 1, we just need to flip this particular bit, so we will use XOR operation for that. So if it would have, if that bit was 1, so it will become 0, and that's what we want. And then this makes sense. Okay. And then we have to calculate over all the cases, all the valid cases. We have to add them. Plus key. And then just return this state. Okay, so let me see. So what we have done is, so for every idx man, I'm selecting every jth woman and seeing if they both are compatible, and that woman has not yet been selected. That means its bit is still 1. Then I am selecting that woman over here, making the mask equal to that bit equal to 0, since flipping the bit, and I'm going to the next man. And when all the men are done, we will see if all the women are selected, then it is a possible matching, and otherwise it's not. And then this is there. I think this is good to go. Let's just see this. Sorry, line number. Oh, sorry. Mask, whatever. What I was doing. Mask, and mask, my bad. So this is actually the state which I'm trying to memorize, right? -2. Okay, now I think this should be fine. What? Let me just see. So we have done this, and then we have input the matrix 0th index. What's wrong in this? Oh, my bad. So I have to even reset the DP state also to 0. So finish. Okay, cool. So this works for this only one option. One, that's right. For this. So if this one is fine, then minus. Oh, alright. There should be modulo also somewhere, right? Yeah, modulo is also there, right? Because this would exceed the integral range, right? So that is a problem that can be solved easily. And constant and mod equal to 189 plus 7, and then just make it as this. This is one, this is one, this is one, and then over. Now we just need the percentage mod, and then I think we are good with it. One zero two 1560. Yeah, and that looks good. So let's just submit it. So basically, before I submit, let me summarize it for you guys. And this was 21 only, right? Okay, so yeah, this work, it's well within the limits. Alright, so before we submit, let me summarize it for you guys. So basically, it was just a basic recursion with memoization, but for the state we needed to know that which woman is particularly selected or not, and for that we could have used an array for that, for just making the index ones or zeros, but we cannot memorize the array. And since we know that n was to 21, which was well within the limits of 10 to the power 7, in the case of memory I was saying, so it was 10 to the power 6. 2 to the power 21 was something around 10 to the power 6. We can use an integer for that, and that's basically what we call a mask. And through the mask we can actually bitwise, we will know, like bit can work as ones and zeros, and we can treat it as a boolean to know that if that particular index is present or not. So that's when we say whenever a problem of bit masking, DP bit masking comes, it's basically referring to this concept only. Okay, so now let's just submit it and check how it goes. here also. So that's there, it is going 13, 15, 16, 17. Yep, cool. It got accepted. So that's one of the problems solved, which was DP by bit masking. Now let's jump to the second problem, which is the div3f problem from Codeforces, maximum byte subtree. So first I'll read through the problem. It says you are given a tree consisting of n vertices. A tree is connected undirected graph with n minus 1 edges. Each vertex v of tree has a color assigned to it, av equal to 1 if the vertex v is white and 0 if the vertex v is black. You have to solve the following problem. For each vertex v, what is the maximum difference between the number of white and the number of black vertices you can obtain if you choose some subtree of the given tree that contains the vertex v. Okay, the subtree of the tree is connected subgraph of the given tree. More formally, if you choose the subtree that contains count w white vertices, count d black vertices, you have to maximize count w minus count v. Okay, and n could be as big as 10 to the power 5. So by this constraints, it is simply says that the answer should be log n log n or order of n. Time complexity for a solution should be this. So basically what the problem says is there are some white vertices marked by 1 and some black vertices which are marked by 0, and we have to, for every particular vertex, we have to maximize the count of white vertex and count of subtracting the count of black vertices in its subtree. So for instance, so this tree is basically 1 2 3, yeah. So first example, this is the first example. So basically and what it is saying that we have to do it for every vertex, right? Okay, so for now let's just forget that part, and for every vertex let's just fix with one vertex which is actually which we assume to be a root. Let's just assume for now the root is 1, right? So now for 1, what would be the answer? So for 1, the answer would be we have to maximize the count of white vertices minus count of black vertices in its subtree. So clearly we don't want black vertices, we want more of white vertices. So we have to select a subtree such that white vertices are more than black vertices. So we won't select this part, so we can say the subtree could be this, all white. And we can even select these both because you see they are not actually contributing much because they are getting nullified by each other only. If there would have been one more white vertex here, I would have taken this also as a part of my subtree, then it would have been all this, because then the number of white vertices would have increased. So we can ignore them also, or we can have them. So for now let's just say, for simplicity, let's just ignore them. So finally our subtree will be this. So these 4 nodes. So the answer would be count of white would be 3 nodes and black is 1. So 3 minus 1 is 2. So for first, as you can see, it is 2, right? That works. So for now, if I would have said, if I would have asked you guys, let's just consider subtree which is below it only, not above. So for 2 I am saying subtree is below this only. For 4 I am saying that subtree will only have this one node which is 7. For 1 its subtree would be actually present. Now what the problem was actually wanting was, for 2 the subtree could be, since it is not a rooted tree, subtree could be the whole tree, and we had to select the valid subtree which provides us the maximum answer of count of white vertices minus count of black vertices. But for instance, let's just so basically these kind of problem, I use a technique of rerouting, and there could be multiple ways. I will show you two ways to solve them, and for that also I will go one by one. But for that, let's just say we fix the so one of the ways is rerouting, in which we reroute the tree. But let's just say for starting we just fix one tree one node as the root of the tree, and then we solve the answer for it, and similarly the answer for its subtree vertices also. Like for example, by that what I mean is, like I'm saying 2, so for 2 it will assume the subtree for it is the number of vertices below it. For 3 the subtree for it would be 4, 5, 7, 9. Alright, so we will solve it like that. So we would say, by doing this, for 1 we will have the answers, but for other vertices we'll have the partial answers, but because we don't have the answer for the rest of the tree which is not below it, right? And we will find a way to how to solve that also. So let's just do this also. Alright, so wow. Okay, so the nature of the input is n, first the n number of nodes, then the color of each node. 0 means black, 1 means white, and then every node connecting to each other, 1 to 2, 1 to 3, and it's 2 into 10 to the power 5. Okay, so for this kind of problem, let's just say we have a dp1 table which will store the result 1, 2, 3, 4, 5, which will store the result for, as we said, that we'll select one particular node as root, which is 1 for now, and then we'll calculate for every node in its subtree, we'll calculate the answer for it, and we'll just assume that the subtree is just below that node, not above that node. We will solve the above part later on, and then we can just say so basically maybe I'll draw it and show you what I'm trying to say. So whenever I'm saying, so assume this is a tree, right? So for this node, since it is not rooted, for this node its subtree would be the whole tree, right? Similarly, when this node is there, its subtree truly will be not just this part, but will also be this part. So if we transform this to, then it would have been, if this was node A, B, then this would have been something like A would have been with B, and then this node, and then these both node would have been here, right? So this node would have been B, this node would have been A. So that's what I'm saying. This would be the actual subtree for this node. But for now we are saying that let's just forget about the above part. Let's just assume that subtree is below it only. So for every particular node we'll have the subtree below it. Okay, so coming to the original question, and we'll have them stored, its answer stored in dp1, and then we'll create an adjacency matrix again corresponding to these many nodes, maximum nodes, and then just write code integer n comma x comma y, and then C N. Okay, we have a color array also, which will be storing color of every particular node. Now once we have that, now we'll input the tree, which is vertex wise, edges wise it is saying. So we'll just do that. I equal to 0, I less than n minus 1, I plus plus. There would be n minus 1 edges, and then we'll have two vertices which are connecting each other, and then we'll just push them into our adjacency matrix list. That is done. Now once we have the tree as the input, now we'll calculate the solution for the first part, which I said we'll calculate. So for the first part, we'll calculate for every particular node what is the best possible answers in its subtree, which is down below, only down below, of how many maximum of white minus black. So basically we want white nodes more than black nodes, and maximum number of, and the maximal value of that, right? So for that we'll run a DFS and then to iterate through the tree, and we'll have int node and parent node. And then we'll just do DFS of, we'll assume tree to be rooted by 1, so we'll start with 1. And then what we actually want is, we want to have white nodes more and black nodes less. So we'll have that, we'll store the difference of white minus black, and we need to maximize that. So assuming, so if this particular node, dp of node, will be equal to the color of node is equal to 1, which means it is a white node, then we'll have 1 as the answer, 1 white node. Otherwise we'll subtract 1 black node, 1 will subtract. So basically dp of this, it is storing count of w minus count of black node, right? So we'll subtract. So basically if there is only 1 black node, then the answer would be minus 1, right? So we are subtracting that. Now what we need to do is, we just need to iterate through the adjacency list of this node. Plus, we just need to check that we are not moving back to the parent. If it is not equal to the parent, then we need to just go to the child. Node of I, so now the parent will become this particular node. And now we will store the answer for it, right? So how the answer will be there? So let's just say we were calculating for this, right? and this was a white node. So it was saying I'm having answer as white. Now this would be returning, it would say, let's just say it just says 2, which means since there are 3 nodes, it would say there were 2 nodes below me which were white and 1 node which below me which was black. So answer is 3 minus 1, which is 2. So I'm passing you 2. So the answer for it would be 2 plus 1, 3. Total 3 white nodes and 1 black node, right? So 2 plus 1. And if it would have been minus 2, then do you think we need to use it? We don't need to use it, right? Because it is having more number of black nodes. Why should I even use it? Does it make sense? Yep. So okay, so one of the things which I was thinking about is, we could have thought that okay, this one is black, this one is black, and maybe this is white, and then we are we are not choosing -2, but we could have chosen this one. But if this would have been white, the answer for it would not have been -2. We would have not selected these 2 black nodes for this, because then they would have contributed -1 and -1, right? So that's what I was thinking. I was just thinking maybe I'm going somewhere wrong, but it's alright. So we would be, if adjacency, so basically dp of adjacence adjacency of node I if dp of adjacency of node I is less than 0, then I don't, if it is greater than 0, if it is greater than 0, then only I would want it as an answer for me. Otherwise, why do I even care, right? I won't select it. And then dp1 dp1 of node will be plus equal to dp1 of adjacency of node I, right? And then this holds, and then we can just return. This is what we have done. So doing this, we can have the answers for this subtree which is below it, and for root 1 we can have the answer. So let's just I equal to 1, I less than equal to n I plus plus. So let's just verify it. See out dp1 of I and then alright, everything right. Let's just see what it produces. Oh, so it is sync 3, which is, I think, which is wrong. It was, oh, it was, yeah, it should have been, no, it should have been 2, 3 minus 1, 2. Somewhere we are going wrong. For 1 it should have been 2, because 3 white nodes and -1 black node otherwise, and my answer, it is giving 3. So somewhere we are going wrong. Okay, let's see. Oh shit, I had indexed the color from 0 at index. but whereas the vertices are numbered from 1 to n. Okay, so now let's just see. Yeah. So for, let's just go through. For first index the answer is 2, which is right. For second vertex the answer is 1, basically selecting this because this subtree does not make sense to, it does not make sense to select because both of them are black. For 3 the answer should be 2, right? For 4 selecting these two only, or even these two, but they'll both nullify each other, so it doesn't make any sense. 2. For fourth we have 1, obviously selecting this. 7, choosing 7 does not make sense. For 5 the answer is 0, yeah, obviously. For 6 the answer is -1, obviously selecting this. 7 answer is -1, 8 answer is -1, 9 answer is 1. Cool. So we have done this part perfectly well, but now what we want is actually we don't want just the, okay, so now what we have done is we have calculated the subtree perfectly, but we don't want that. We just want, for this particular vertex we have done calculation till of this part, but we need to have this part also. So one of the way to do it, which I would actually both, I would say both are from the same concept, both follow the same concept of rerouting, but implementation wise and think like how quickly you can think, this one, the first one is, I would say, comparatively easy. And so the concept which I use over here is rerouting. So what by rerouting I actually mean is we subtract, okay, so for, let's just say, do we have commands there? Yeah, cool. So for rerouting what I mean is I have, so this is the root which I had selected initially. Now I will make this tree as this node as the root, and if I make this as the root and I have the answer for this, I have the actual answer. So how to make this the root? So first we'll disconnect this particular edge from this tree, so this will get isolated, and how we will, and then we'll try to add this particular root to this particular vertex and make its child. So first we'll remove this particular node's contribution in the root, so we have disconnected this edge, and then finally we will just add this particular vertex into this particular node so that it becomes its child, and then we have the answer for this whole subtree, right? And this is the concept of rerouting basically. So how we will do this is through this ydfs1 integer node So for that we will need one more DP array first. And then whenever this particular, and dp2 would be the final answer, so dp2 of node is equal to dp1 of node, and that's the answer for it. So for initially the root has the answer for itself, so dp2 is the final call, right? So for root we already have the answer. Now we'll create its child as the root node, and for that what I'll do is I'll just again reiterate through the code. And now what we need actually to do is we have to remove its child contribution from the parent node. So basically dp1 of the node, we will remove its child contribution, and we will only remove, since we have, if its child was contributing greater than 0, then only we had added. So similarly we will remove then only. So if dp1 of adjacency of node comma I, dp1 of adjacency of node comma I is greater than 0, then only we will remove it. Otherwise we'll remove 0 from it, right? You don't need to remove anything. So now we have disconnected the child from the root, and now we will actually have this child become the root, and this root node we will make its child. So basically dp1 of adjacency of node I, we will have its contribution added, and we will have its contribution only added when we will have its contribution only added if dp1 of node is actually greater than 0, then we can have its contribution added, dp1 of node, otherwise we'll have 0 added. And that's it, and we have created, and this has become the new node, the new root node, and then we'll just pass it dfs1 additions of node comma I, and then now once we come back for the other child, we have to reset the whole setup first to the initial setup. So we will do it the same, and just in the order we had done it earlier. So we'll first detach its contribution, and then we'll recreate the original root again, adding it, and we have recreated the whole setup again as it was, and now we can do it for the next child, the same thing, and then that's done, right? And then we will have the answer in dp2. I think everything is right, so let's just check. Okay, something went wrong. dp1 of node, I don't understand. Maybe let's just do some debugging and see what is happening. What? Ah, come on. I haven't called only DFS2. Sorry, DFS1. I think this is not needed anymore. Yep. So somewhere we have gone wrong. 222. Somewhere we have gone wrong. Yeah. Now let's just see where possibly we could have gone wrong. This is there. So dp1 we had calculated it properly, dp2 we have gone somewhere wrong. So first we check from the root node if its child had contributed. What is this? Yeah, what is this, man? If its child had contributed something, then we will have that. Otherwise, remove this. Yeah. 102. Yep, I think this is right. Just copy this one. Yes. 0 minus 1 1 minus 1. 0 minus 1 1 minus 1. So that is also right. So I think, yeah, we are good to go. Let's just submit it and see. We can just good. And then we have it submitted, right? So we have got it accepted, right? And then we can have and then we can have one more kind of. Okay, so now I'll show you one more way actually solve it, which is kind of where one can say not. It is also basically saying the same thing, but maybe not that much intuitive. In this we will just, as we had done it over here, for any particular node if we had some other. So we had calculated this dp in dp1 for below, and whatever from outside, like from up, you can say from up of this node is coming, we didn't know. So we'll have a variable named up which will store all this value and provide it to it, and then we can solve the problem again, right? So similarly we'll have a variable called up, and then let's just, for root node we don't have anything from up, so we have 0, and then dp2 of node would be equal to, we'll say dp1 of node plus whatever is coming from up, and then that's it. And then we'll again just iterate through the tree. But now we have to actually pass the node from top, value from top which is coming. So now let's just say we go to one of its child. So one of its child, so now what value would have come from top? So the same thing of rerouting only, but we will create top variable which will say value from top would be dp1 of node, which is the original node. You subtract the value from this particular child, which is dp1 of adjacency of node comma I, and you only subtract, you say if the value is positive, which is maximum of zeros comma this positive value, if it was also positive value, you subtract that value from this. So this is, and then so basically this would have, and if something from top to that this particular node have come, we add that. I think this is right, and then we just pass it to the DFS2 adjacency of node comma I comma node, and then let's just again, we want positive values only, so for, I think this would be positive only because I have made sure. No, this could be negative because let's just say all this is 0, but dp1 could in itself be a negative value, since let's just say it's black node, but we don't want black node to contribute anything from top, so we'll just pass positive values, and then that's it. And then I think this was also good to go, dfs2 dp2. Okay, let's just see, 0 1 minus 1, right? And then yep, that was also working. So let's just submit this one also. Where is the practice? Credit CPP. It's in practice only, right? Yeah. And then with 45, 53. And then it got accepted. Okay, so these were the two problems basically which I wanted to cover. So so one was DP with bit masking and the other one was DP on trees, and this concept is actually, I would say, a nice concept of rerouting. It could help you. I've seen many problems of the same concept, so this could help you. I guess I was clear with my explanation. Alright, so that's all from my side. Thank you.